Oh my gosh!
All right, guys, we have, hey, focus. Haley, Chris, come on. Right here. We started going through these. Yesterday we talked about if the A value is smaller, when that value right there is smaller, it is possible to get negative numbers. Negative values of R make inner loops or tiny loops. We saw that on limacons with inner loops. So again, when it looks like a limacon, which it does except for the 4 with the theta, if I take away that 4, it's a limacon with inner loop. So when you see this with that 4 right there, or a 3 or whatever, this means that you're going to have some tiny loops. When it's an even number, like before, you're going to have those loops in separate places. When it's an odd number like 5, the loops are going to be in the same place. So here, 4 means there's 8 loops all in different places. You saw that kind of with rose curves. When you had 5s, we said that there were 5 loops, but the reality was, ooh, and I didn't show you this. Check it out. No, when A is bigger than, when A is smaller than B. What is happening? Okay, I want to show you something. I've got my little calculator here. I mentioned how when you graph these polar graphs, it's hard to see. We'll see if this shows up. Yes. Okay, this is an old 84. The sole advantage of the 84 is that its brain is much slower. So let me just give you an example. Normally you would look at this and think, oh, it's a rose curve, right? This is not an A plus B. This is just a B. So rose curve, and you see that too, and you would know that there are 4 petals. And you could find where that first petal is by saying, well, where would cosine of something be 1 so that R is maximized? And you know that cosine is 1 at 90. I mean, at 0. You set 2 theta equals 0, solve, you get 0 degrees. So I know I have a petal at 0. The 2 says I have 4 petals. They're all equally spaced. So when I go to graph this, tell you what, let me make this. I think this is going to make it better looking. You can see it going through all 4 of these petals. Inspire, you can't see that because it just goes and spits it out real quickly. But watch when I make it an odd one. So when I make it an odd, there are 6 petals, but you'll see it trace over itself twice so that you only see 3 of them. You seeing that? So there's always double the number of petals, but sometimes you just don't see them because it's tracing over itself. Well, when I get to a problem like this, where it's 2, say, plus 6 cosine, I'll start with 2 theta. When I look at that, I think, oh, well, there's probably 4 petals again, double the number of petals. But in this case, they could possibly be 8 long, 2 plus 6, right? But if cosine is a negative 1, does that make sense? Because if cosine's 1, the R value would be 2 plus 6 times 1. It would be 8 long. And I can find out where those are by saying, where is cosine 1? Well, cosine first petal is at 0. So I know there's going to be there's going to be petals, 2 petals that are actually long, okay? But there's also going to be 2 other petals that are going to be actually short. And when you see something like this, you can see the 2 long petals and the 2 short petals. And the short petals, if you go back and look, the short petals always result when you have negative R values. You can see this if I trace. Look at this. I'm tracing through the degrees right here. Notice these R values. Actually, it's hard to see that. Let me make this better. 360 mode degree. I'm going to make my step. Let's just make it a cool 30 degrees. Oh, that doesn't work. Let's make it a cool 7.5 degrees. That'll be kind of decent. But watch when I trace this thing. There's 15 degrees, right? There's 30 degrees. And you can see at 30 degrees, my R value is positive. There's 45 degrees. It's a positive R value. And then here's 60. Now, 60 degrees, I'm not located at 60, am I? So what must have happened? I'm at 60. R is negative. R is negative on those little loops. And look, it stays negative all the way through there. And then once I hit somewhere in there is 120. There's 120. But then look, now at 127, well, look, 127 is back to positive. That's 127. I'm moving in a positive direction. And then I stay in a positive direction all the way through that. But then look right here at 240. Well, 240 is down here. Why am I going that way? Must have been negative R values. So if I can have negative R values, that's when I'm going to have little bitty loops. That was true if I traced a limacon with an inner loop. Check it out. Here is a limacon. When it's a 1, it's a limacon with an inner loop, right? But look at this as I'm tracing. Positive, positive. These are all angles all the way through probably 90. Nope, all the way through whatever. So actually right there at 105, you can see I still have a positive R value. But now I'm entering the loop. Well, clearly at 120 degrees, that would be a positive. I have a negative R value. All these little bitty loops result from negative R values. So if you're wondering which graphs have little bitty loops, there are always going to be graphs that could possibly have a negative R value. And the only way to have a negative R value is what? When you have an A and a B. For the B to be bigger. If they're the same, I can't get a negative. I can get a 0. If the first one's bigger, I can only subtract smaller numbers because the cosine can't be bigger than 1 or smaller than -1. So literally the only way I can have these little loopy graphs like I'm seeing here is to have a smaller A value, whether it's a limacon with inner loop or whether it's one of these modified looking rose curves. So here, but you can kind of use some of that same mentality and say, wait, if that's a 4, there's 8 petals. But wait, there's only 4 petals that are going to have big maximum values of 8. And then there's going to be 4 other petals that have R values of -4, which still are going to look like they're out 4, but they're technically -4. And because they're even, we tend to see all of them, don't we? If you think about rose curves, when it's an even number, we see all 8. Now, if your brain's exploding on that and you really just want to know where to mark them, well, you can do the math. Check it out. I could say, all right, R will be 8 when what? R will be 8 when that is 1. So where is cosine of 4 theta equal 1? Now, the answer is really when the 4 theta equals 0 plus 360n. So where is it going to be 1? Well, when theta is 0 over 4 plus 90n. So we're actually going to have 4 petals starting at 0, then at 90, then at 180, then at 270. Man, I don't want to do so much math. I just would rather notice some patterns and make my life easy. So all of these little notes that I give you on these are trying to show you the pattern so you don't have to do all this math. But I can mark all the petals there if I want. So this means that on this graph, I'm going to go out that way, that way, that way, and that way, 8. Now, if I want to redo this and say, okay, now where is cosine -1? Because if all of that's -1, I get R values of -4, right? So where would it be -1? This is going to be the small petals. At 180. So I could change that to a 180, and I could divide by 4 and get 45. So this tells me at 45 degrees, I need to go back 4. And then when I add another 90 at 135 degrees, I need to go back 4. And then if I add another 90 at 225, I need to go back 4, -4. And then finally at 315, I need to go back 4. So I can do these all day long using this mentality, all of these weird ones. And if you want to know the math, that's probably a safer bet. It might take you a little bit longer, but it's not like I'm giving you 100 of these on my test to graph. But my point is, you can still do these using this math because it's the math you technically already know. We covered this in Algebra 2 and in Trade, how to solve cosine of higher angles.
You're all like, yeah, I remember.
Hopefully you remember some of that, right? So my point is you can do it, but the way my thinking is in a memorizing kind of way, I can also say, oh, if I see this, Oh, it kind of looks like a limacon, smaller number. Ooh, there's a 4 theta. That's one of those rose curves that have big petals and small and the little petals because that's smaller. So where are they? Well, the first one maximizes when cosine's 1, I mark it at 0. And if there's 4 there, there's 8 petals. Oh, 4 big, 4 small. Mark the big ones and then go in between them, mark the small ones. And I'm done. And I didn't have to do any algebra or any trig. So that's what this thing ends up looking like. 4 big ones there. And the reason why that's so sketchy is I made my step too big. How about 3.5? There. So you can see that 0, there, and then 45, there. Y'all seeing that? So anyway, again, trying to show you some patterns on this. But anyway, let's go back and start. Now, cosine graphs. I'm sorry, odd numbers. Now, the odd number is a little bit different. And again, if you're trying to notice patterns, I kind of think to myself, what did odd ones mean before? It meant I only had 5 petals, right? But the reality was I really had 10 petals. They just showed up in the same spot. Well, now with these weird kind of A plus B cosine and theta graphs, sometimes the same spot might be bigger or smaller, right? So if they're bigger or smaller, they might be in the same spot, but you'll actually see them. So I remember, okay, if it's an odd number, I will have 5 or whatever that odd number is, big petals, and the small petals actually are in the same spot. But if you want to toss all that to the wind and just go, wait a minute, let me just think algebra-wise. Where would this graph, let's just look at this third one right there. Where would this graph be maximized? Ask yourself that question. Heck, go to this one, this fourth one. Where would this be maximized?
90.
It would be when R is 8, and what, right? When R is 8, 2 plus 6, what would that have to be for that to be an 8? Okay, so let's think. So where would sine of 5 theta be a -1? When the 5 theta is 270. And you can use -90 if you want. 270, but not just 270. 270 plus 360n, right? So really the theta ends up being what? 54 degrees plus 72n? Because I'm solving for theta. So where's the first big petal? At 54. So I go to 54 and I mark it. And then if that's 54, I add a 72 and get 126. I add a 72 and get, and then I keep adding 72s to get those values, right? And then I go back and say, oh yeah, but where would it be minimized? It would be minimized when it's a -4. That would have to be what? +1. And where's +1 occur? At 90. And when I divide that, what do I get? I get 18, right? No, hold on.
Wait a minute.
Yeah, but I don't see it. Hold on. 5 theta equals 1. Oh, yes. So at 18 degrees, which is about right where?
There.
About right there. I go what? Back. No.
Weren't you supposed to go back on the other one?
Yes, the R would be -4. So at 18 degrees, I go back -4. And then at 90 degrees, I go back -4. And then I go back -4. And I keep going back. But again, you can do that math, which makes it harder, right? This is where R is a -4 when that is a 1. You can think through that, or you can go, wait a minute. For these curves, when it's odd, the small petals are just inside the big petals. And then you don't have to do that. So again, I'm showing patterns. All these patterns, I'm talking about them down here. And I know that's a lot to read. I really created these for hey, go home and read this and see if you notice. But you'll notice with these, that the process and everything is very similar to this next grouping. So what do you see on this next grouping? What do you see here? No, talk to me up here. What do you see? Now the A value is bigger. If the A value is bigger, guys, is it possible to have a negative petal? No. I'll go one step further. Is it possible to have a R that's 0? No. So this can't hit the pole at all. And if it can't hit the pole, what you need to do is figure out, well, let me figure out where the biggest places lie, and then let me figure out where the smallest places lie, and then I can just zigzag in between those points. So this is a little different, but again, with the same thinking, what would be the biggest value of R here?
8.
R would be 8. Now, where would that R value of 8 actually occur? Let's think about it. R would be 8 when that is a 1. When would that be a 1? When 4 theta is a 90 plus 360n. So I could divide everything by 4, and I'd get theta equals 22.5. Now, I probably wouldn't do all of that. I would probably just find that first one, mark it at 22.5, and then I would think again, well, 4 theta means what? It normally means 8 petals, right? But if you really think about what the 8 petals meant, it meant there were 8 places where it was either maxed or min. So this is a little bit weirder, but if you did the whole formula here, you would get plus 90n and C, 22.5, whatever that is, 112.5, 201.5, or whatever. You'd go through there and get those 4 places where it is 8. Where would it be? What would the R value be if it was minimized? 6 minus 2 would be 4. That's as small as the R value can be, right? Y'all seeing that? And when would it be 4? When that's a negative 1? Where would sign be a negative 1? How about negative 90 just to help my math? But yes, 270 works. And then when I divide 4 into that, I get negative 22.5. So here is negative 22.5, but I'm doing what? I'm sorry, this would be an R value of 4. Yeah, no, that's right. No, at negative 22.5, I'm going R equals 4. 1, 2, 3, 4. And then I add 90. Or subtract 90, whatever. Right? Because I can't get a negative 4 in this one. I can get a 4 when R is negative 1. I can get an 8 when R is positive 1. But either way, I've marked the points. Sketch. Now, I can do this thinking for all of these graphs. I don't have to do really much memorization. And the more you do it, the better off you'll be. But the more I get into these uglier problems, the more you're going to have to be able to think this way. Jump over to this third one. It's a cosine graph. So what is the maximum that R can be? 8. When would R be 8? When that is 1. When would that be 1? When 5 theta is 0 plus 360n, and that would occur at 0 plus 72n. So the R values of 8, the big ones start at 0, there's 8, and then you add 72, add 72, add 72, add 72. Well, that worked great. I got my 5 big petals, right? Now, where would the minimum value, what would the minimum value of R be? Positive 4. Where would positive 4 occur? If that was what? A negative 1, that could be a positive 4. Where is cosine of negative 1? 180. Divide by 5, 36. So at 36 degrees, there's 30. So 36 might be maybe right there. I'm going to go R equals 4. 1, 2, 3, 4. And then every 72. There's my petals are highs and lows anyway. Connect the dots. You just got to know that when it's 6 plus 2, you're going to be connecting into this little starfish looking thing. When it's 2 minus 6, what happens?
You have in the it would be rows.
2 minus 6, you're going to have big and small petals. But you could literally do this math. Again, it didn't take me very long to find the places either way. That's what I do for these. And then the last grouping you have is this, which you notice is what? When A equals B, what's the biggest value of R you can have?
0. Oh, no, the one in front.
When minus 2 and 2.
8. Why 8?
A plus B.
Because if that's a 1 right there, if that is a 1, then I get 4 plus 4 times 1, which is 8. So ask yourself, where would these petals, now if you're looking at this and going, why isn't that just a rose curve? Good question. What would the end value be? Like if I just said, wait a minute, these go out to 8. Why isn't this just a rose curve? I don't know, maybe sine. Why wouldn't I just go, well, what do I do for 6 petals? If I put a 6 on a rose curve, how many petals is it supposed to have? 12. If I put a 3 on a rose curve, how many petals is it supposed to have? 3, because it's odd. So how do I make 6? I'll tell you how. Like this, or with a weird lemniscate. You can do it with a lemniscate too, but we don't do those kinds of lemniscates. So right here, I look at it and I go, well, if I want to graph this, R would be 8 when sine of 6 theta equals 1. When is sine of 6 theta equal to 1? When 6 theta is 90 plus 2 plus 360n, right? So when theta is 15 plus 60n. So there's my 15 degrees. I go to 15 and then I add 60, 60, 60, 60, 60. Right? Now, what's the smallest it can be? When that's a negative 1, right? So 0 occurs here, but can I get a negative value? I can't get a negative value. I can't do that unless the lead number is smallest. So that means there are no little petals. There's a bunch of zeros. But how do I draw a petal which has an R value of 0? Like R could be 0 when? When that's a negative 1? So I can go to negative 15 and go, all right, I'm at negative 15. Let's mark an R value of 0. Add 60. Add another 60. All right, it's not doing anything. So the little tiny petals evaporated, kind of like an inner loop evaporated on a cardioid that also had A equal B. So the other 6 petals just shrunk to nothing and they're gone. Are y'all seeing that? So anyway, this is how you would graph a 6-petaled rose curve. Now, when you get to these, if I gave you a picture of that, there's really no way you would know whether that was a sine rose curve or this kind of weird sine rose curve. Because I can make a 5-petaled rose curve, can I? So this one also is 5-petaled. But so either I would have to take either formula. I made a note of that if you read. But again, if I saw this, I could go, all right, what's the maximum R value you could have?
8.
Where would I get an 8 if that was what?
1.
And where would that be 1?
90.
At 5 theta equal 90 plus 360n. And then if I divide by 5, I get 18 plus 18 plus 72n. So I start at 18, add 72 to find my other 5. Now, where would the little petals occur? Oh, wait, the little petals, I would be minimized when R is a 0. Well, R is of 0, who cares where they are? They have no length. So I just mark it at the pole and connect my 5 dots. That's all the polar stuff that you would ever see at a math tournament. Stopping at lemniscates, not counting this other stuff, is all the polar you would need to know in pre-cal, regular pre-cal, or BC Cal. In BC Cal, you actually do area of these things. We don't get into integrals of polar graphs in AB. But in BC, you'll have to know your polar pretty well, but I don't think you do anything with these. Or if you do, there's a game plan for it if they give you weird polar graphs.
Mister, do you know what Wordle is?
Wordo?
Wordle.
Wordle?
Yeah.
No.
Really?
What is it? Is it some app that everybody's addicted to?
No, it's
Yeah,
it's
like
a new website.
It's a word game. It's
And
on
New York
Google.
Times
It's-
just bought it.
You can only play like one a day, and it's like you guess a word and it tells you which letters are like in the word in the right place, which letters are in the word but not in the right place, and which letters aren't in the word at all.
I'm surprised you don't know.
And you try to guess it in 6 guesses.
Is there a mathurdle?
No, actually, there is math too
It's
if you
called
think
Nerdle.
about it. Because if you
Nerdle?
think
I don't
about
like
the
it.
statistics
Wait,
of
so
what
There's a bunch of different.
No, I haven't heard it.
Really?
Text me the link or something.
Any word?
Any word.
Yeah, but
Don't
okay.
do something
Pick a
stupid,
word
like-
with a bunch of
I already got to Wordle today.
So,
All right, hey guys, what about
No,
these?
it's not like that. I got it.
I got it.
I mean, what did I just do? These are all the sign ones.
The likelihood that O is first and N is last is very.
So guys, all of these, hey, I put all these little tricks for you
'Cause you
to
can
know
see-
where they are. But the bottom line is, look, on any random one, if I said graph it, I'm just going to pick this randomly. If you really want, you can go, what would be the biggest value of R? That's where the big loops are. What would it be?
8.
8. Where would R be 8?
Add 0 or well, that's equal to 1.
When this is equal to 1, where is that equal to 1?
0
Add
plus
0
1.
plus 3 into the word.
When it's equal to 1 is when the 5 theta is 0 plus 360n, right? So when the theta is 0 plus 72. That's really all you have to do to find these petals. So if you really want to condense it all, then no more math. If you don't like the trig and that bothers you, then notice the patterns. But at some point, you do have to recognize, I can't get a negative R value out of this. I can't, but I can get a 0, so it is going to hit at a pole. Okay? And remember, negative R values give you the little bitty loops. And then up here, right here, I can't get a negative R value out of these, can I? In fact, I can't even get a 0. So I need to know where I peak or where I trough, like furthest, smallest, but I can connect those dots. But I'm not going to have little inner loops here. I'm not going to have any loops, any petals really on these, because I can't get back to the pole when that number is bigger than that number, right? But again, I can set these equal and go, all right, where do I get furthest away? Where do I get least furthest away? Mark those points connected. And then when you get something like this where I do have an A value smaller, on these you're like, oh, well, not only can I maximize at 8 at certain places, find those, but I could also get negative R values. Those are the little loops. Find those. And you can do them the same way. Again, randomly. I'll jump to number 4. Again, if I want to forget all my rules, I could go, where would R be 8 right here? R would be 8 when?
5 theta is negative 1.
When that is a negative 1. Where is that a negative 1?
Negative 90 plus 260.
At negative 90 or 270 plus 360. Where does that occur? At negative 18 plus 72. Mark your 18 and start adding 72s. And then you go back and go, all right, what would be the smallest value of R? A negative 4. When would R be a negative 4? When that is a positive 1. In this case, it might be different if there's a plus, but in this case. So where is sine of 5 theta a positive 1? At 90 plus 360n. Now you got to be careful here. I do get 18 plus 72n again, but this time it means at 18 degrees I do what? That 4. Oh, those are in the same spot. 72, 72, 72, 72. So all these rules I have for pattern recognition, great. Or forget it and just do the algebra. And at some point you kind of start getting it. It's probably a safer bet, I think, to just think through the algebra. That way you can do every problem similarly. And you don't have to go, wait a minute, what kind is this? Oh, wait a minute, what's the... You can just really eyeball it and look at it and go, all right, talk about biggest, smallest R value. But if, again, on this last set right here, there is no way, nope. There is no way on these for you to get a negative or even a 0 R value. You're not hitting the pole. On these, there are no loops. And if there's no loops and you're not hitting the pole, it almost looks like a bunch of dimples, like on a dimpled limacon, which again, dimpled limacons are when the A value is bigger than the B potentially, or maybe convex. But you see a bunch of high-low spots and you got to find those markers. All right. Okay. So we ran over a little bit. I'm not overly worried about it. But today we're supposed to be working on or talking about what? You know what? I'll give it later.
Oh, this one.
Hey, which one are we looking at?
D odd.
D odds. You're supposed to have it done, right? All right, let me go over the D odds with you. And then on Monday, I'll give you the key once you get done with the evens. So I'm going to read off the odd answers for you. One, this is D odds. One, y'all with me, guys? One is D. One is D. 3 is E. 5 is A. 7 is D. 9 is C. 11 is B. 13 is A. 15 is C. 17 is C. 19 is D. 21 is A. 23 is B. 25 is B, 27 is B, 29 is A, 31 is C, 33 is A, 35 is C, 37 is E, 39 is A, 41 is, ooh, and 41 was rough. Is B. Well, I mean, the math was easy once you figured it out, but it was rough to figure out. 43 is, I think it took Helmer's 3 days. 43, and then something clicked with it. 43 is, did anybody get that, by the way, 41?
No,
I know.
Yeah.
I did, but I didn't.
I got it.
I was like, that looks about right.
I was one.
Hey, and you
off.
know, sometimes that might be the way to go. Draw something really to scale. Hey, I've gotten stuff that way. No shame in that.
I got it.
None at all.
I was one
Points
off
or
and I
points?
guessed.
Yeah. What were the answers?
Yeah.
It was 50, 125 was the right one, and then it was 200 minus 8 times root 29,
Ooh, that's close.
200 minus 20 root.
Yeah, that'd been hard to guess because the 200 minus 8 root 29 is about 150, 60. It'd be, yeah, I think it'd be hard to eyeball that without a really accurate picture. But anyway, but I'll show you the math. It's not a big deal. You'll look at it and you're like, huh. 43 is B, 45 is C, 47 is B, and 49 is D.
I got like a whole 3 right.
What was
I
47?
got 3 correct. I don't know. I didn't even know how.
All right, now again, our goal is to get better, right?
Wait, what was 3 and 5?
3 was E, 5 was A.
I thought I got 5.
This is test D, right?
Yeah.
Okay.
Yeah. Yeah.
I got D as well.
Oh, I got B. B.
I circled up the ones that I would put down on
B
the
has
test. Just kidding, guys.
All right, guys. So if you have a question, which I'm hoping you do, let's talk about D in our remaining time, the odds.
Number 5.
The odds.
Yeah, can we do like a quick kind of review over probability?
I think we should be able to do 37, but I didn't know.
I don't know if I can do. Yes and no. Actually, if you look at your assignment sheet, we're doing a little probability. Oh no, the next one. We will have a review of probability before we take the state test. We will. It's a little 3-day cram session.
Mr. Hurd, can you do 37? I feel like I should be able to
Okay,
do it.
D number 37.
No.
Yeah.
Thank you.
Is if x is 2 sine theta, which of the following is an algebraic expression for cotangent of theta? So 37, I am going to solve for theta. Hold on, 37, let me read it again. If x is that, what is cotangent of that? Okay, so I did this. So 37, I said if x is 2 sine theta, which is what they gave me, then the sine of that would be x over 2.
We can't see the board.
Oh.
Sorry.
So if x is this,
Then laptop is equal to 3,000.
You draw the triangle, and the radius would be 2 because the
Triangles have radius?
Or not the radius, or like the.
What triangle? I think we're doing 37.
hey, you can do that, Bailey. You actually don't even have to watch. If you know that the sine is this, cotangent is cosine over sine, right? So really, if I can write it in terms of sine, everything, if I can, now, but you can do that. But if I can, I think, if you write it in terms of sine, which I can, right? Cosine over sine. And then I use the Pythagorean identity, which was cosine squared plus sine squared equals 1. I subtracted the sine squared and square root of both sides. So that's the cosine value. That's the sine value. And now I have everything in terms of sine, and I can just put x over 2 in there. What she's saying, which might actually be a little easier, she's saying, well, what if you just said, hey, if I had some triangle like this, and that was theta, the sine of that would be x over 2. Well, then Pythagorean theorem would say that this is 4 minus x squared, right? right? So right here, if I want cotangent of theta, which was cosine over sine, I could say, well, the cosine is that over 2.
Man, that's so much easier.
And then the sine is already x over 2, and the 2's cancel, and I get that over that.
Bailey, why did you say it was a quadratic form?
Well, because to find the 4 minus x squared, I had
I meant Pythagorean theorem.
to. Oh, wait.
Yeah.
I know the formulas, I just don't know what they're.
So yeah, I actually think that's probably a better way. This is just where my brain led me. But yeah, I think what Bailey was saying was probably a little simpler to just draw a little triangle out representing what you know, find what you don't, and then you know you can represent any trig function of theta by a ratio. So yeah, I kind of like that better actually. What else?
Can I just make a quick little comment?
Sure.
You know, at NYU, they teach a Taylor Swift class.
Wow, that is so
Oh!
I've learned
That's
so
pretty
much
interesting.
about math.
Are you going to?
What else you got?
Did it do number
5.
5?
5 asks. 5 question multiple choice quiz. Each question has 4 possible answers. You forgot to study it and are going to have to guess. What's the probability that you get an 80% or better? So 80 or better. So 80 or better means what's the probability that you get 4 out of 5 or 5 out of 5, right? Right? I can't, 3 out of 5 would not be an 80. That would be a 60. So 80% or better, this would have to happen. So I would, if you think about the probability of being correct on a 4-question test is 1 out of 4. You in the back, you guys probably haven't learned this. This is what we'll do in our crash course, this kind of thinking. So what it means is if you got 4 right and 1 wrong, then you would have 1/4 times 1/4 times 1/4 times 1/4 times 3/4. All right, that's 4 right, 3 wrong. However, who says I have to do it in that order? I don't have to get just the last one wrong. I could get the first one wrong and the next 4 right, or the first right wrong and then the next 3 right. How many different ways are there to get 4 right and 1 wrong? Well, that's this combination. That's like counting the letters in Mississippi. How many ways can I get right, wrong organized? Are you following me? So that counts all this up. And when you multiply it out, that gets you the probability of getting 4 right. Probability of getting 5 right is 5 correct, none wrong. You don't have to put 0, 3/4 to 0. And then that would be 5 right I'm arranging. Well, clearly, if they're all right, how many ways are there to get all of them right? 1. Well, that's what this ends up giving me is 1. But when I add those 2 together, I get 1 in 64. So you had to figure out what possible ways could I do something 80% or more. Those are it. And then find the probabilities of each. So that's what happens when you have independent events where one choice doesn't affect the other, right? And obviously, flipping a coin, randomly picking questions. If I miss 5 in a row, is there any better chance of me being right on the next one? No. If I pick 4 non-aces out of a deck, is the next pick going to be more likely an ace than the first one? Yeah, because there's less cards, right? You have there's more aces in the stack if I'm pulling up. So independent, dependent work a little bit differently. These are independent. Yes.
You do 13.
Yep. So 13 says just simplify that. So where am I? 13. Okay, so 13 to simplify it. I've noticed some things about 1 plus i's. And I have this memorized. And if you don't have it memorized, just remember that you can do it. 1 plus I, when I square it, gives me a monomial. Monomials are easier to raise to powers than binomials. Look, if I square that, I get 1 squared. That times 2. And then the I squared. But the I squared is what?
-1.
And the -1 and the 1 cancel. So all of this is 2i. If I do the same thing with 1 minus I squared, I end up getting -2i. Now, if you forget what and memorize those, don't worry about it. Just do them real quickly and then go, all right, how can I rewrite this as a bunch of 1 plus I squareds? Well, I have 1 plus I squared to the 8th would be 16 of those, right? So I'm going to do that with an additional 1 plus I to represent those. Why is this helpful? Because now I can take this and replace it with 2i. So when I replace it with 2i, I get 2i to the 8th right there with an additional 1 plus I. Well, I do the same thing on the bottom. How can I deal with 1 minus I to the 16th? Well, it's a 1 minus I squared to the 8th. And I can square 1 minus I squared. It's negative 2i. So at the end of the day, I look at this and I go, wait, I don't even have to go 2 to the 8th is 256. I to the 8th is 1. I don't even have to do that because all I do is look at these two and go, wait, this 8 on the bottom would have made that positive, right? Well, then they're the same. And everything cancels and all I have left is that. So usually you can simplify and clean stuff up with that whole, how can I rewrite? And listen, you're going to see these all over the place. I mean, they do this 1 plus I thing or 1 minus I thing a lot. Now, the real way to do it is it De Moivre's theorem? I forget all it does. All right. It's remember where we took a imaginary number and we wrote it in polar form, right? We looked at this and said, oh, well, the absolute value, the magnitude, like is a root 2. And then we went cosine. If I go over 1, up 1, imagine that's 45 degrees. Do you remember doing this? Writing it like this and then raising this to the 16th? Do you remember that form where you raise root 2 to the 16th, and then you multiply the angles by 16, and then you simplify it and get an answer? That's kind of what they're suggesting that you ought to do, but there's an easier way to do it. So whenever I see 1 plus i's and 1 minus i's, I rewrite them as squares, make those substitutions, and then simplify that. And it usually simplifies pretty well. And you remember what happens if you get a big I value, like here you only got I to the 8th, but what would happen if you had like I to the 35th? You remember how you can rewrite those? If you divide the power by 4 and just keep the remainder, those are equivalent. And if you're wondering why, every I to the 4th is 1. And this is just a bunch of I to the 4ths with a few extra left over. And if every I to the 4th is 1, all you have left is I cubed. And then I cubed, if you struggle with memorizing those, that's just an I squared times an I, so a negative I. But as long as you know how to simplify those, these are very doable. Like everybody in here should get that on your state tournament when that shows up, unless there's some weird quirky variation, which I don't know that there are. Yes?
Can you do 31?
Sure. Maybe. I immediately look at those and I go, ugh. Okay.
Geometry killed me. I didn't get a single one. A single geometry was right.
All right, so 31, here's my picture. So they gave me 0A, C, and B. They told me that AB is a perpendicular bisector, so I know that those two lines have a 90-degree intersection angle. It says if AB is 8 root 3, so that tells me that this section and this section are 4 root 3s, right? And then it tells me, blah, 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 what is the area of the circle? Okay, so if those two right here and right here are 4 root 3s, what I did is I just labeled those X and those Y. Okay? So I thought, all right, if that's the case, I can create a system out of this. Now, this is just me being kind of clever. It's really more algebra than anything. I clearly know that if I did this and label those, I don't know if I know they're not the same, right? X and Y. But right here, that is a right triangle. So I can say that squared plus that squared equals that squared if I want. Now, also, and by the way, you could have done this a little differently.
Yeah.
Isn't Y and 2X the same? So if that radius is the same as that radius, if Y is 2X, I can make a substitution in there for Y equals 2X and solve. Now, the other way you could have done this is just from the very start. If you're going to call that Y, you could have called this Y over 2 if you knew that, right? And then you could have just said Y squared equals Y over 2 squared. And then you could have just solved for Y. And once you have Y, you can go back and figure out what those X values were and figure out what the radius is. So that might even have been easier right there, but you are going to have to solve for y and then go back and figure out what that radius is. Actually, if you solve for y, you'll have it. Is that what it asks for? Well, it asks for area. So right here, I could say, if I had done it this way, which again, probably would have been better, I'd get y squared over 4 plus 48. I'd probably multiply through by a 4. 1's 92. So I get 3y squared equals 192. Y squared equals 64. So y squared. So pi y squared. Done. So much easier if you just make that substitution and don't overthink it with a system like I did.
I did it a little bit differently. There's like the property of the 30, 60, 90 triangle. It's like the sides are A root 3, and 2a. And so if A to B is 8 root 3, that means like A to that middle point is 4.
Oh, no. Yeah, sure.
And then you can just multiply it by
Sure.
2. And then
Yeah, if you noticed that. Yeah, I didn't catch that. That's good.
Will you do
Good.
27?
Good.
Don't remember.
Number what?
27.
27. All right. Okay. This is a little formula that Helmers goes, oh yeah, that's like apostrophes formula. Blah, blah, blah. Whatever. So I'm looking for my finger here. I didn't learn this stuff, but he said, hey, anytime you have a situation like this, if you label that A, that B, that C, that D, the A plus B times the B is equal to the C plus B times the D.
What number is it?
27. So I didn't know that. So clearly I was stuck. But if you do know that, and they gave you everything but D, right? So I just said plug the numbers into that and solve for D or for X or whatever. And it can't be negatives, it must be 2.
Can you do 11?
But again, that would be something you have to memorize from geometry. I'm guessing you probably did learn that when you were with Helmers, but I didn't have Helmers. So I say it again, 11.
11, yeah. What is multiplicity?
Okay, multiplicity means it happened more than once. So if they say you had a multiplicity of 6, that means the root was 2 6 times. So here's one way to do it. Number 11. Number 11 said this ugly polynomial has 2 as a multiplicity of 6. So what I did is went, well, what are the sum of the roots?
Of course.
The sum of the roots is negative b over a. We should know that from our summer readings and things like that, or maybe even go back to Miss Tyree, but I know I talked about it in Algebra 2. Well, if the sum of the roots is 6, right? And I know I have how many roots? 7, because it's x to the 7th, right? Well, I know that the sum of the 7 roots is 6. But if 2 is a root 6 times, then I can plug those 2's in and solve for the missing root. The other way is to synthetically divide by 2 all the way down until you get one last thing to solve and you get 6.
Yeah.
Hey guys, evens over the weekend. Be ready on Monday for the evens.
I'll figure out what I need to know. I'll spend 10 minutes being like, dude, if only I knew how to do these 4 geometric things.
Dude,
Like,
you don't remember that little flip book that I made in 8th grade?
flip
Triangle.
Yeah,
I don't.
with the triangles.
Nope.
I probably still have that.
Oh, I know the 3069 and the 9045.
I don't know what they mean, but I remember talking about it. I'm just not good at geometry. I don't like memorizing, and I'd rather figure it out.
Well,
Wait, are we supposed to?
No, he's in that.
All right, y'all good.
You too.
The freshman didn't